Start recording right now? Okay, so we just started recording. Hi, everyone. My name's Chris. It's very nice to be here today. It's very much an honor to be teaching so many people at once over this virtual setting. And even though it's a rough time right now, I'm glad that we could still all come together and learn some chemistry and get ready for your exam. Francis just wanted me to let you all know that this will last from 6 to 8 p.m. and we're going to take a 2-minute break at 7 p.m. to thank the healthcare workers. Take a 2-minute break. If you need to use the bathroom or anything, that'll be a good time. Is there anything else that you need me to say? Yeah, I can hear you. Okay, well, can I just get started? All right, thanks. Okay. All right, so hello everyone again. My name's Chris LaMartina. Just a little bit of background about myself. I'm a current first-year graduate student at Columbia University. I'm pursuing my PhD in organic chemistry. Right now I work for the chair professor of the chemistry department at Columbia. His name's Tom Rovis. That's my full-time profession. And then right now, I'm helping out Frances giving this AP chemistry review session. She requested me to help you guys out. I received my bachelor's of science from the California Institute of Technology, aka Caltech, which is out in.
This is the AP chemistry review session Daddy wants you to do. He said he's coming back.
My SAT now.
All right, I think someone's
All right.
Anyway, I'm just going to be talking a bit louder right now over everyone. I assume since this is over Zoom, there's a good chance that I might get interrupted at any moment. So if that happens, then we'll just carry on afterwards, which is fine. So like I was saying, I did my undergraduate at Caltech. I just graduated 1 year ago, and I've been back in New York ever since. I'm originally from Forest Hills, Queens. I was born and raised there. I went to Forest Hills High School, and while I was at Forest Hills High School, I did go to Queller Prep because originally I wasn't doing too great at trigonometry. And then I joined Queller Prep, got a tutor, started learning trig at like an incredibly fast pace, and then did very well on that course. And then I started getting tutored for the SAT exam. And I went through a 1-year training practice course with a bunch of my friends, learning how to take the SAT. Ended up getting perfect math score, which I think helped me get into Caltech because they only take 800s or 780s or whatever. So I have to, give a big thank you to Frances for helping me get to where I am today. And I couldn't be here without her help. I'm just letting you know it's like a long road to get to this point now. I'm much older now. I'm 23, getting my PhD and everything. And most of you are young in high school taking this exam right now. But only maybe 6 years ago, I was in your spot taking this AP chemistry exam. And I was really nervous for it because I love this subject so much. And if I got anything less than a 5, it was more of an ego thing than me actually trying to get credits. And I just wanted to prove myself that I could, do very well in this subject. So I studied extremely hard for this AP chemistry test. I think I took it in 2014 and I ended up getting a 5 on the test, which was pretty good. And then turned out from there that, I found a passion in chemistry when I went to college and I wanted to major in it. So I got my bachelor's in chemistry, and really what it came down to was doing research in synthetic chemistry labs. So me being in an actual lab, making molecules and everything. So that's what I do now as my professional job. And it's really like a dream come true, but I'm just saying this would have not been possible without the help of Frances Queller. So, without further ado, I'm just going to get started with this actual review session. So I've prepared a PowerPoint today, and we also sent out a pretty comprehensive review packet. So the review packet is more supplementary material that you could study up on your own. This is more something for you to read before your test to help you out. but I'll be focusing on presenting this PowerPoint today. And this is gonna help you give, I'm gonna help give you test taking strategies, and we're gonna be covering particular questions. So I'll be covering about a dozen multiple choice questions in depth, covering key concepts, and then some of the short response questions. And so let's see here. So yeah, so just in terms of exam logistics, how the exam is actually set up right now. The section 1 is all multiple choice questions. So it's 60 problems, which you will be able to do in about 90 minutes, and that's 50% of your exam score. The questions are either discrete questions or question sets, so you'll have some data that will be provided and you'll answer questions about it, or you'll just have to use some raw intuition to figure it out. And students are provided with a stimulus or set of data and a series of related questions. And also you cannot use your calculator for section 1, so all the math will be pretty easy and straightforward, which is fine. And then for section 2, this is, I would say, the harder part of the test is the free response, which is 7 questions. Then you have, hello? Yeah? Okay, I still don't think people could hear you, Francis. Okay, so I've just been notified that this is the format from last year. And for this year, due to the coronavirus pandemic, the test is now 45 minutes. Yeah. Okay, so the test is going to be shorter this year, which is lucky for you. Right, so I'm just going to hop into the actual material instead of the course logistics. So in terms of topics on the exam, there's 9 main topics covered in organic chemistry. And of course, there's many subtopics within each one. So what did you say? Okay. Thanks. Anyway, so the first 7 topics that I have here will be covered, being atomic structure and properties, and then molecular and ionic compound structures and properties. Number 3, intermolecular forces and properties, so things that affect boiling point. 4, chemical reactions in general, so how to balance equations and stoichiometry. 5 being reaction kinetics, so the speed of reactions. 6 being thermodynamics. 7, equilibrium equations. 8, acid and base chemistry. And 9, electrochemistry. And I did include some electrochemistry in this review because I was unaware that this may have not been on the exam this year, but it's still worth knowing. So like I said, in this review, we're going to be learning together by working on multiple choice questions and free response questions from previous exams. So I've been pulling actual questions that people have taken in the past. And so when we're covering these questions, I'm going to be talking about the key concepts of each question and the thought process of quickly answering these questions, because time is of the essence. You have a very short amount of time to take this exam, even shorter than usual. I'm used to taking 3-hour AP exams, but apparently now it's going to be 40 to 50 minutes. So don't spend too much time on one problem, which could prevent you from answering other questions later in the exam. And most importantly, stay confident and trust in your skill set. There's a lot of times where you'll spend, months and months studying for a test, and then you'll get to the actual exam and you'll let that fear or paranoia take you over, which is totally understandable. Test anxiety is a very real thing, but it's important to just stay confident in your skill set and be able to take the exam without doubting yourself, right? So in terms of materials that we're giving you during the test, of course, you get your periodic table of elements, and we'll be talking about the different trends and properties that you could get from this table, and it's very iconic. And then also you're given this set of reference material And so a bunch of equations and values of different constants and what these abbreviations mean. And so at this point, you should have seen this in your studying and be familiar with this kind of reference packet. Anyway, so we're just going to hop straight into some multiple choice questions that I pulled out from the 2008 exam.
Hi. So Chris, I just want to let you know, I figured out why I was on mute before because you and I were in a call. So just to remind you, and again, Chris took the test years ago, it's just going to be free response. So just keep that in mind. We'll jump into free response questions.
Okay, I'll get to the free response, but the actual multiple choice here still covers a bunch of important topics.
Okay,
Yeah,
but everyone in the group listening, yeah, sure. Everyone in the group listening, please remember this year, just go over the format again, just because it's different. So it's going to be free, 1 or 2 free response. Go ahead.
Okay, so I'm still going to be talking about multiple choice. I already prepared this presentation, so I'm not going back now. And still, the concepts that are covered in multiple choice questions could, of course, appear in free response questions, right? So still important. So we're just going to hop into some multiple choice questions that I pulled from a 2008 exam. So over here, questions 7 through 9 refer to the following pure substances, which are gases at 25 degrees Celsius or room temperature in 1 atmosphere, so standard temperature and pressure. So number 7 is asking, for starters, which molecule has a pyramidal shape? So in terms of the key concept that's covered here, we're going to be talking about molecular geometry. And so molecular geometry is the 3D orientation or shape of molecules that you could usually guess based on valence shell electron pair repulsion theory, or VSEPR, right? Which most of you are probably familiar with. And so in general, lone pairs cause repulsion that bend groups out of plane. And so in terms of trying to figure out,
Alexa's on.
I think someone is talking. Anyway, in terms of trying to figure out the shapes of each of these individual molecules, it's important to recognize ahead of time which molecules or atoms actually possess lone pairs in their structures. And that could be deduced based on your periodic table as well. So someone has just drawn a line over my, I'm not sure where that came from. Anyway.
Yeah, it's fine. We'll just keep going. Let's go.
All right. So in terms of drawing these out, right, we'll notice that these nitrogen containing compounds, so let's say in this case, NH3 is ammonia, which usually is found in the liquid phase, would be trigonal pyramidal, because generally you'll start with 3 groups coming out of your nitrogen. However, you have this lone pair that actually pushes down all 3 of the hydrogens out of the plane. And so instead of getting all your hydrogens in the plane, like a trigonal planar structure that's directly to the right, so BH3, for example, you're going to get a trigonal pyramidal structure because you have the lone pair actually repelling all 3 of the hydrogens down and forming kind of this piano stool kind of looking structure, right? Versus a BH3 structure, which actually does not have a lone pair. It has an empty p orbital right on the boron instead. And then you're going to have all of the H's perfectly in plane, and all of these will have 120-degree angles versus the trigonal pyramidal structure, where you'll be closer to somewhere between 109 and 120 in that range for the trigonal pyramidal. And then for linear compounds, it's quite simple to see. For H2 hydrogen gas, or HBr, these would be linear because it's just 2 atoms together with 1 bond. And if you have H2S, or an equivalent structure would be water, where you have 2 lone pairs on the central atom. Instead of having a linear compound, again, these 2 electron pairs are going to repel the 2 hydrogens out of the plane. And so you're going to get a bent structure instead of a linear that you might anticipate that you would get. So therefore, the answer in this case would be A. You would have a lone pair on the nitrogen that causes trigonal pyramidal geometry. And then this is dependent on you being able to draw Lewis dot structures and being able to see what kind of repulsion you're getting with, based on the valence shell electron pair repulsion theory, right? So that one's pretty straightforward. In terms of question 8, what is a strong electrolyte in aqueous solution? This involves knowing the definition of what an electrolyte is. And so the key concept here would be the chemistry of solutions or homogeneous mixtures. The difference of a homogeneous mixture and a heterogeneous mixture being homogeneous, it's all in the same phase. So let's say you take salt, for example, and dissolve it in water, like NaCl, in your kitchen. All of the salt is going to dissolve completely into the water, and you're going to get a homogeneous mixture. Versus if I were to mix water and oil together, these phases cannot actually separate with each other due to the polarity difference. And so that's why water and oil actually can't mix with each other, because you're forming a heterogeneous solution. So they're actually in 2 separate phases. And that would be the difference. So any solution is actually just a homogeneous mixture. And so an electrolyte is an ion pair that can dissolve as a solution in water or another liquid, right? So what I mean by this is that when you introduce this solute into your solution, are you going to be able to completely dissociate your compound into its ion pair? So like I was saying, if you take NaCl, which is a salt, when you dissolve it in water, you're going to get Na plus ions and Cl minus ions in solution, right? So the question here is asking which molecule could form an ion pair in water. And so we would have to look at each of these and see which could dissociate. So if you look at NH3, if you know about ammonia, it's usually a liquid and forms very strong hydrogen bonds. And so it's not actually going to dissolve into an ion pair in water. BH3 is also not going to do that, because you would have to be breaking a boron hydrogen bond, which could be quite difficult. Hydrogen gas is extremely stable atomic elemental gas, so that's not going to happen. And then hydrogen sulfide is also not going to dissociate to an ion pair. However, HBr, when you dissolve it in water, is going to form hydrobromic acid, right? And we know that acids give off protons, which are actually H plus in solution. So the measure of how acidic something is the concentration of H plus or protons that you have in solution. And so since HBr, when you introduce it into water, it goes from hydrogen bromide gas into hydrobromic acid, which is a very strong acid, meaning that it completely dissociates in water 100%. And you'll generate a very strong ion pair, which is actually a strong electrolyte. So when you're drinking Gatorade, for example, and you're getting advertised that it has a lot of electrolytes in it, all that means is that it has a bunch of salts inside of it. And generally, water can only conduct electricity if it has ions in it, because that's how you get your charge in the water. So actually, pure distilled water cannot really conduct electricity well, versus if you add a bunch of salt in water, it conducts electricity much better. That's why it's an electrolyte, right? So in this case, the answer would be E. Hydrobromic acid dissociates into its ion pair. And then for question 9, is asking what's the slowest to effuse through a small opening at 25 degrees Celsius and 1 atmosphere, right? So the key concept here would be kinetic molecular theory, or the properties of gaseous particles. And so effusion refers to the movement of gas particles through a small hole, and the effusion rate of a gas is inversely proportional to the square root of the particle mass. And all this means is that the heavier your compound, the slower it'll effuse, right? So you're gonna have to be looking at which compound actually has the highest molar mass, which you could calculate by looking at your periodic table and deducing each molar mass. But we actually know that bromine is on the heavier side. So again, the molar mass is about 81 grams per mole. The answer will be E again. In this case, hydrogen bromide has the highest molecular weight of any of these compounds, so it'll effuse the slowest in its gaseous form. Okay, so in terms of reviewing some thermodynamics, which we'll be doing a lot today because that's a very prevalent topic, it's giving you a bunch of enthalpy and entropy values, so either positive or negative. So greater than 0 meaning positive, less than 0 meaning negative. So for 12, it's asking about the enthalpy and entropy of a reaction that is spontaneous at all temperatures. So the key concept here again is thermodynamics, and we're just going to briefly cover some definitions. So enthalpy describes the total heat content of a thermodynamic system. So an endothermic process is going to be a positive enthalpy value, meaning that heat is added into the system. So you have some external heat source that you're adding into your thermodynamic system. And exothermic, meaning heat is released from the system. So if you run your reaction, you're actually emitting heat. Entropy describes the disorder of a system or the degree of randomness. So a positive entropy value or a positive entropy difference, the entropy of a system increases, meaning your disorder increases. And if you have a negative entropy difference, then the entropy of the system has decreased and you have less disorder. And in terms of Gibbs free energy, which is the third important thermodynamic value, this describes the spontaneity of a system and relates enthalpy to entropy through the equation delta G equals delta H minus T delta S, which is the very important equation that you should be familiar with as well. And so Gibbs free energy describes the thermodynamic favorability or spontaneity of a system. So a positive delta G difference means that the reaction is non-spontaneous or thermodynamically unfavorable or will not occur on its own. And then a delta G that's less than 0 means the reaction is spontaneous or thermodynamically favorable. So in terms of all of these definitions, for a spontaneous reaction at all temperatures, you need delta G to be less than 0 or have a negative value at all temperatures. So now you're going to have to look at the equation and see, based on the signs of delta H and delta S, under which circumstance will you always have a negative value of delta G? So in general, spontaneous reactions are exothermic and have increasing disorder. And so if you have delta G and you have always a negative delta H or an exothermic process, you're always going to have a positive temperature because it's in Kelvin, and you're going to have a positive entropy difference, meaning increasing disorder. This will always give you a negative value of delta G. So the answer has to be C. So in general, if you have an exothermic process that also has increasing entropy or increasing disorder, the reaction will always be spontaneous at all temperatures, which is important to know. So the answer would be C in this case. In terms of question 13, it's asking what is true about the evaporation of water at 25 degrees Celsius and 1 atmosphere STP. So the evaporation of water, which we're all familiar with, occurs actually spontaneously at room temperature and requires thermal energy to do so. So if you just leave a cup of water out on your desk and let it go for, I don't know, a day, you'll come back and notice that there's less water in your cup because it's been spontaneously evaporating. And so water is also going from the liquid phase to the gas phase when you're doing this. And so considering that, if you have thermal energy going into your system, you'll actually realize that this is a endothermic process, right? So heat is added to the system from the air. And so you're actually heating up, let's say, a cup of water from the heat in the air. And it has a positive entropy difference, so more disorder in the gas phase. So you have increasing disorder going from a solid to a liquid to a gas being the most disordered in the air, a liquid being in the middle, and then you have a solid being the most ordered in a crystal, for example. And so the answer in this case, for when you're considering the evaporation of water, would be A, because you have an endothermic process that has a positive entropy difference, right? So this requires some intuition of knowing about how water works as well. Okay, so now in terms of question 14, what is true for the combustion of liquid pentane to form water and carbon dioxide at 1 atmosphere? And so we've all heard about combustion reactions before. And so a combustion is the reaction of a hydrocarbon or a compound containing only carbon and hydrogen with oxygen, O2 gas, that always generates water and carbon dioxide as the products. And so we know that setting organic materials on fire, let's say setting a piece of paper on fire, releases heat. And pay attention that again, you're going from the liquid to the gas phase in this case again, because you're going from a liquid pentane to gaseous water and CO2. So in this case, combustion reactions are always exothermic and have positive entropy difference. So the answer is going to be C again, which you'll notice is true about a reaction that is spontaneous at all temperatures. So combustion reactions are always spontaneous. So keep in mind, whenever you light something on fire, it's just going to go by itself. All you have to do is add a little heat and you have oxygen in the air, and then that's how you could easily set things on fire. And so generally any organic compound you could set on fire quite readily. So in terms of question 20 here, in solid methane, the forces between neighboring CH4 molecules are best characterized as what? And so the key concept here is considering intermolecular forces, or what allows a liquid to be a liquid, what allows a solid to be solid, what forces are holding these molecules together. So let's just discuss each definition here of each from A through E. And so in terms of ionic bonds, these are formed between two ions with opposite charges. So a good example would be salt, again, NaCl, or magnesium bromide, or some positively charged metal and a negatively charged halogen. And then you'll have ionic bonds. Generally, these will be solids. Covalent bonds are an interatomic linkage that results from the sharing of an electron pair between two atoms. So for example, CH bond or an NO bond, generally between carbon and some other atom will generally result in a covalent bond, right? So these are actually, ionic bonds and covalent bonds are not intermolecular forces. These are forces that hold together atoms. So these are real bonds. And so in terms of intermolecular forces, we could have a hydrogen bond, and then the strongest intermolecular force is a hydrogen bond, which is a bond between two molecules resulting from an electrostatic attraction between a proton or an H in one molecule and an electronegative atom being oxygen, nitrogen, fluorine, and the other. So examples of molecules that have a lot of hydrogen bonding, water. And so because the hydrogen bonding in water is so strong, the liquid form is quite stable on its own. And so due to the hydrogen bonding in water or ammonia, these are able to exist as liquids at room temperature, where usually for small molecules, you would expect a gas. Then you could have ion-dipole forces, which are an attractive force that results between the electrostatic attraction between an ion and a neutral molecule that has a dipole. So for example, if you have calcium ions dissolved in water, all of the oxygens in that water, in that solvent cage, are going to be pointing towards the positively charged calcium ion. This is a definition that doesn't pop up too much, so I wouldn't worry about it. And then more importantly, London dispersion forces are the weakest type of intermolecular force and a temporary attractive force that results when the electrons in two adjacent atoms occupy positions that make the atoms form temporary dipoles. So imagine you have an electron cloud in some nonpolar molecule, and your electrons are kind of circling around in these orbitals, and you're causing little divots in this electron cloud. So for a very short amount of times, you'll have positive and negative charge accumulate that rapidly dissipate as well. So this is actually the weakest type of intermolecular force. So in terms of methane, you'll have to realize based on its structure, which you will have to draw out, methane's a symmetrical tetrahedral molecule where all the CH bonds have small dipoles, but they cancel out because they all point in opposite directions, and they make the molecule in total nonpolar. So there's no net dipole or positive and negative end on a methane molecule. Therefore, its intermolecular force must be through dispersion forces. So recognizing when a molecule is nonpolar, you will generally have London dispersion forces that are keeping it together. None of the other answers here make sense. CH bonds can't make hydrogen bonds. And if we're talking about ionic bonds and covalent bonds, we're talking between two atoms. But in this case, we're talking intermolecular, meaning between two molecules. So the methane is going to have London dispersion forces holding it together. And so in terms of question 21, of the following electron configurations of neutral atoms, which represents an atom in its excited state. And so its key concept here is electron configurations. So let's just discuss the ordering of orbitals based on patterns in the periodic table. And so if you're looking at the periodic table here, you could actually deduce the exact ordering or energy levels of orbitals as you're going along. So you'll start with hydrogen and helium that have a 1s orbital. And then on the far left, you have what's called the s block. And then on the far right, you'll have the p block. And in the middle, where the transition metals are, you'll have the d block. And so if you're going from left to right and down on the periodic table, that's actually the order in which you're going in. So you'll notice it goes 1s, 2s, 2p, 3s, and that's just going in order, reading left to right on the periodic table. And so remember that an s subshell has 1 orbital, could hold 2 electrons. A p subshell has 3 orbitals, which could hold up to 6 electrons. And a d subshell has 5 orbitals, holding up to 10 electrons. And you must completely fill 1 subshell before populating the next one that is higher in energy. And so an excited state configuration will have 1 electron from a lower energy level pushed up to the next highest energy level. So you have to be able to recognize what is in its ground state and what is in its excited state. So in this case, I've drawn out a little orbital depiction for you. The ground state configuration could be 1s2, 2s2, 2p6, right? You're going to fill up a p orbital with 6 electrons before you go up to the next highest energy level. And that will be the ground state configuration. If you excite it, then you're actually going 1 electron from a lower energy level and bumping it up to a higher energy level. And so in this case, you'll have an excited configuration that you could see in answer B. And so B should be a dead giveaway because you have 5 electrons in a p orbital and you're already filling up the next orbital, which would not make sense for a ground state configuration. And so if you are able to relate a ground state configuration to its excited state configuration, generally you'll be able to deduce what is in this excited state. And then this is just a little schematic showing you electron excitation into a higher energy level. And a lot of chemistry that's going on nowadays, like what's going on in my lab, results on this kind of principle that you could take different energy levels and push up electrons from lower energy levels to higher energy levels. It gets pretty interesting. Anyway, so for question 25, in terms of pressure, an atmosphere is exerted by 1.85 molars of an ideal gas placed in a 3-liter container at 35 degrees Celsius is given by which of the following expressions. And so this relates to the ideal gas law, which is the master equation that relates pressure, volume, moles, and temperature through a very simple equation and very elegant equation. PV equals nRT, PIV nert is a nice way to remember it, the ideal gas law. And R is the ideal gas constant, and you're given this value in your reference sheet. So to solve for pressure, all you have to do is solve for P. And so you could rearrange this, right? And just get P equals nRT over V, and then plug in all of the values that you're given. So this is just directly plug and chug, essentially. And so also keep in mind that we're converting 35 degrees Celsius to Kelvin because you need Kelvin to apply into this formula based on the units of the ideal gas constant, right? So in this case, your answer is going to be A because what I've drawn on the bottom here corresponds to what's on the left for A. And so this is a very straightforward, just math equation. And so for question 35, which of the following changes to the equilibrium system represented above will increase the quantity of hydrogen iodide in the equilibrium mixture? And so the key concept here is going to be Le Chatelier's principle, which is an extremely important principle to know for AP chemistry. You definitely have to know this front and back. So the principle can be used to predict the behavior of a system under equilibrium due to changes in either pressure, temperature, or concentration. And so some of these questions can be difficult because you have to mix and match some of these problems. So just look at each of these as kind of like a true or false kind of situation. So in terms of the definitions, if you're applying Le Chatelier's principle, a change in concentration means if you add additional reactant, let's say on the left side of a system, it'll shift the equilibrium to the right towards the side of the products. And by the same logic, reducing the concentration of any product will also shift the equilibrium to the right. And the converse is also true. So all I'm saying is, let's say if I were to increase the pressure of hydrogen iodide gas and I increase it, it's going to start shifting the equilibrium to the left, to start making more reactant. So you just have to be able to orient yourself and recognize, are you shifting equilibrium to the left or to the right? So in this case, for adding hydrogen gas, you're increasing the concentration or pressure of your reactants, and thus you'll be shifting your equilibrium to the right-hand side and generating more product, right? And in terms of changes in pressure, a change in pressure or volume will result in an attempt to restore the equilibrium by creating more or less moles of gas. So for example, if the pressure in a system increases, conversely, the volume decreases, the equilibrium will shift to favor the side of the reaction that favors fewer moles of gas, right? So similarly, if the volume of a system increases or the pressure decreases, the production of additional moles of gas will be favored. So the key for change in pressure is that it only works if you're in the gaseous phase, right? So you're gonna have to look at total moles based on the stoichiometrically balanced equation. So in this case, I have 1 mole of H2, 1 mole of I2, right? So that's 2 moles of gas total on the left, and then I have 2 moles of HI on the right. So I have 2 moles on the right. And because the molar concentration of these gases are equivalent on both sides in this case, you actually get no difference based on Le Chatelier's principle. For example, though, if I had 3 moles of gas on the left and 2 moles of gas on the right, and I increase the pressure, then I would shift the equilibrium to the right to alleviate that pressure. And then in terms of change of temperature, this comes down to if your reaction is endothermic or exothermic. So the effect of temperature on equilibrium has to do with the heat of the reaction. So for an endothermic process, or delta H is greater than 0 or is positive, adding heat will shift the equilibrium to the right. So you could imagine heat as a reactant, right? And you're increasing the concentration of this reactant, or in this case, you're increasing the heat. And so you will actually shift the equilibrium to the right in this case. And then for an exothermic process, you're releasing heat. And so adding heat will shift the equilibrium to the left in this case, right? So keep in mind an equilibrium reaction is going both ways at the same time. So you just have to be able to recognize if something is endothermic versus exothermic, keep that in mind. And so the answer in this case is going to be C based on what we've been talking about. So for this particular reaction, adding H2 will increase the concentration on the left and thus create more products on the right. And you would shift the equilibrium to the right, making more HI. The reaction is endothermic, meaning you're increasing or you're adding heat to make the reaction go. So increasing the temperature will also shift the equilibrium to the right. In terms of pressure, the total moles of gas on either side is equivalent, 2 moles on both sides total. So changing the pressure or volume will have no effect on the equilibrium in this case. And so only 1 and 2 are true. And so the answer would have to be C. And so Le Chatelier's principle will definitely show up again, and I have a short answer question that also discusses Le Chatelier's principle. So if this doesn't make sense on a first-hand basis, I would go through that packet that I sent and really study up on these definitions. I'll also be sending out this PowerPoint afterwards. So if you want to study from this PowerPoint, I will give access to everyone. So you could read it on your own later. And so for question 45, in this case, we're talking about heating and cooling curves, right? So the cooling curve above shows how the temperature of a sample varies with time as the sample goes through phase changes. And we'll be discussing what this means right now. And so the sample starts as a gas, and then heat is removed at a constant rate. So at which time does the sample contain the most liquid? And then you're choosing between T1 through 5. So the key concept here is going to be heating/cooling curves, which you may see as well. So these graphs indicate how the phases of a substance change with temperature over time. So as you increase or decrease temperature, are you going from a gas to a liquid to a solid, or the other way around? So realize that the slants, or the lines with a slope, represent temperature changes during which the entire sample is in a single phase, right? So every time you have a slant, you're only in one phase, so you're either a gas 100% of the time or a liquid or a solid. The plateaus, or where the slope equals 0, represents a single temperature during which a phase change is taking place and the two phases are in equilibrium. So in this case, if we're starting all the way from the left, we're starting as a gas and cooling down the temperature. So the whole way from the beginning up to where the plateau starts, you're cooling your gas down, and the heat of the equation, or the heat of this situation, would be described as Q equals MCAT, or C being specific heat of the gas, and your change in temperature, right? The first plateau is going to be the equilibrium when you're going from a gas to a liquid phase, right? So during this entire plateau, you're cooling down and you're in equilibrium between these two phases. So it's just right the point where a gas is condensing into a liquid. And then when you're cooling a liquid down, in this case, you're a liquid the entire time until you reach the bottom of that slant and you start to reach the second plateau, which represents freezing. So in this case, you have an equilibrium between the liquid and the solid forms. So you're freezing a liquid into its solid phase. So for example, you're freezing water, right? And then at the end, you're just cooling down a solid, and then this slant could go down technically infinitely. You could keep decreasing the temperature and you're not going to get any more ordered than a solid. And so the phrasing of the question is a little odd because it asks, at which time does the sample contain the most liquid? So we're going to have to look at the slants versus the plateaus in this case. And so in this case, the key concept again would be heating and cooling curves. The answer is going to be D, because the most liquid is actually going to be present at T4, or time 4, since that time involves the cooling of a liquid. So all during that slant, you have 100% of the liquid, or the most liquid you could have at one time. Once you reach that plateau to, let's say, freezing, then some of your particles are going to start going into the solid phase. And if you go to the left of that and you start evaporating your liquid, you're going to start getting some particles in the gaseous phase. So you're going to have less water or liquid either on the left or right of that slant. And so T4 is the only time where you still land on a slant, and thus you're going to have the most liquid at that time, right? If I'm looking at T5, this is when I'm changing from a liquid to a solid. If I look at T2 or T3, this is when I'm changing from a gas to a liquid. And if I'm looking at T1, this is the time when the gas is cooling, or probably when you have the most gas available, right? So in this case, this question requires interpreting how a heating or cooling curve actually works, and interpreting at which point will you actually have the most liquid, or most gas, or most solid, right? And you may be confronted where you have a math equation and you actually have to plug in Q equals MCAT, etc. In this case, you would just plug in your values into this equation using the correct units. I don't think I have a particular example of this, but maybe we could talk about it later. Anyway, I think this is the last multiple choice question I have before going into the short response. And so in this case, I have a reaction mixture represented above that is at equilibrium at 298 Kelvin, or room temperature actually. It could be important to recognize when you're at STP. And so 298 Kelvin is actually the same as 25 degrees Celsius, because you're adding 273 is the difference between Celsius and Kelvin. And the molar concentrations are X equals 2 molars, Y equals 0.5 molars, and Z equals 4 molars. And so what is the value of the equilibrium constant for the reaction at 298 Kelvin? And so the key concept here is setting up a KEQ, or an equilibrium equation. And so setting up an equilibrium equation always involves concentration of the products over or divided by concentration of the reactants. And in this case, you're using the stoichiometric coefficients to, and they become the exponents in your reaction, or your equation. So in this case, if I'm doing products overreactants, I'm going to have concentration of Z on top, and I'm going to have the concentration of X and Y in my denominator. And then I'm going to raise each of these concentrations to the respective exponent that is equal to its stoichiometric coefficient. So in this case, you have KEQ equals Z cubed over X squared times Y. And then you'll just be plugging in your values that you have here. So just some very simple math. So I hope you know what 4 cubed is. You'll get 64 over 2, and then this will come out to 32. And so this is a very simple example of setting up an equilibrium equation. However, it's a very important topic to understand in organic chemistry, in AP chemistry. And being able to quickly manipulate numbers and set up math equations will be very useful. And so in this case, for your exam that's on Thursday, I'm assuming because you're on the truncated format and you only have free response questions, you'll have a calculator available and you'll have more time to figure out your math. So that would be quite useful. So I pulled all these questions from the 2008 exam, which we could all recognize was 12 years ago. It was a very long time ago. But I picked these particular questions because I think they highlight topics that will still show up in every year of AP chemistry. So definitely when I took the exam in 2014, all of these topics showed up. And I was grateful to study for them. I guess I'll also mention that when I took AP chemistry at Forest Hills High School, with all due respect to my teacher, he was a great guy, but he wasn't very good at actually teaching the subject, unfortunately. I'm sure some of you are probably familiar with that feeling. So because I couldn't actually learn any AP chemistry in class, I had to do all the studying for this test on my own. And I didn't have a tutor or anything, so I spent extra time studying for this. In this case, luckily there's a review session. However, of course, I'm not going to be able to cover every single last topic here. So that's why I sent out a comprehensive 200-page review sheet that I found online before this that should actually cover every single topic that you need to know in depth. So if you have enough time to skim over that between now and Thursday, I would highly recommend it. And also just taking some practice problems. So if you go to the AP Chemistry website, all of the previous free response questions and the answers are available. So you should be able to go on the AP Chem website and be able to find all of the previous exams. And if you want to practice, then that's a great way to do so. And that's where I'm pulling these questions from and kind of giving you the mindset of how to approach these questions. So I just think in the second hour here, I'm going to want to cover the free response questions, which will probably take another hour to go through. And I think that in about 4 minutes, that's when the
Hi, Chris. I'm gonna quickly join in.
What's up?
I just want to join in and let you guys, just to remind you, as Chris was saying, we have 4 minutes. We would love to know quickly which school representations we have here. So feel free to type in what school you go to. Chris is Forest Hills High School graduates, but he did spend quite a lot of time at Queller. Back in the day, we actually had a physical space that was, what can I say, used. So we do want to share that with you. And we're really happy to know where you guys are from, and a variety of schools hopefully are represented in this workshop. And I guess, Chris, as we're entering the 7 o'clock hour, we're definitely going to take a moment to applaud and to say thank you to every single person into the chat who's a healthcare worker representative. Maybe, Chris, if you could just keep going with some words of wisdom. Those of you who want to take kind of like a bathroom break, you could do that now, because we're going to go back at 7:01. So go ahead, Chris, take over.
Okay. So in terms of words of wisdom, even from my own perspective, I still think that I'm quite young and that I haven't even, really fully started to develop everything that I want to do in my career. Of course, graduating from Caltech and being a Columbia graduate student is an incredibly good start, and I'm super thankful for it. But I'm always looking into the future. So a PhD is a very long time, 5 years, and a lot of people will struggle to make it through all 5 of those years. And, you know, with all due respect, like I also struggle through school. If you're going to the top schools in the nation, you're going to get challenged, you're going to get stepped on, you're going to be humbled. And so if you want to be able to go to the best schools in the world, just recognize that it's always going to be a tough challenge to overcome. So as hard as you think you're studying right now in high school, and as hard as you think chemistry is right now, it only goes up and up from here. Like the skill cap is almost infinite, you know? Even now, after getting my undergraduate degree and thinking that I know so much chemistry, when I meet my professors, you know, they know 100 times more chemistry than I do. And so really the gaining of knowledge and making it through an academic career, you have to take it kind of day by day, step by step. You're always learning gradually over time, but never lose sight of your goals. I want to become a professor when I'm older, and let's say twice my age from now, I'll be 46. And hopefully, and at that time, I'm a tenured professor at some university, right? At that point, maybe I'll consider myself to be kind of old, but even at 23, I still think I'm young and I have a lot of, you know, a big future ahead. And of course, that applies to all of you in the chat. Whoever is trying to pursue a career in the sciences or in liberal arts, or if you're trying to be a doctor, I applaud all of you because it's a very difficult road to go down. But just keep in mind that every single day you have to give this your best. There's sacrifices you have to make, and it's not always going to be easy. And so it's also
Chris,
important.
It's 7. So everyone, it's at 7. Please take a moment to clap into the chat to say thank you to every single person who's here. We want to, yay! And we want to take a minute. We're going to unmute everyone for 1 moment. Okay. And we're just going to, everyone give a round of applause. Yay.
Yeah.
Yay. Thank you to the healthcare workers, mothers and fathers and brothers and sisters and cousins. Yay. I don't hear you clapping.
I'm okay.
117 people who should be clapping. Yay! Can you really say bravo? How about a group bravo?
Bravo.
Oh! Hey! Okay, everyone, and thank you for typing into the chat. And we're really, really happy that you guys are, you know, part of this program, and it means a lot to us. So we do want to share that as well. And Chris, especially, we want to say thank you so much to this opportunity that we're about to enter in the free response questions. And to remember that the first 7 topics are tested, but you should have knowledge, some knowledge of the remaining topics. Everything's interconnected. And we're really grateful that we have so many parents here whose students are participating in this program. The parents are frontline, the parents are healthcare workers. It's really, really impressive. And especially Chris, thank you for doing this. I do want to be clear, this wasn't a week's notice. Did we even have a week? No, right? This was on a few days that we planned this event out. So thank you, Chris.
Yeah, no problem. It's my pleasure.
All right, so we're gonna resume with this, and we're going to go from 7 until I think around 7:50, and then if you could just kind of close up on the most important areas to focus on. And
yeah,
at 8 o'clock, where Chris is going to email the PowerPoint over, we'll send it to all the meeting participants around that time. And I think it's cool to know, I do want to quickly add a fun fact. You should know that Chris and his circle of, I want to say 5 friends back in high school studied at Queller Prep all summer for the SATs. I believe you were the 5 highest at the whole school. Am I correct?
Yeah, somewhere in that range.
So we had the top 5 kids from the school, and they went to Queller and they studied as a group. all summer long. One of them, Josh Dayon's in law school now. Tamir started medical school. And it was a really nice circle of students from years ago. So everyone's moving onwards and upwards. So we're really, really happy that you're here and you're doing this review. And thank you. I'm certain this must have taken you all day to put together the PowerPoint and to review all these topics from years ago. All right, without further
Yeah, I
ado,
haven't looked at AP chemistry in a while.
Amazing. So thank you. Thank you so much for this time and dedication. All right, I'm going to mute myself again. Go ahead.
Right. Thank you for that. And again, thank you to all the healthcare workers right now. It's an extremely important service that we're all grateful for. Anyway, on that note, we'll continue on to some free response questions. So let's see here. Okay, so I'm pulling some questions from actually the most previous exam. So the 2019 test, just 1 year ago when the test was still over 3 hours long. So let's just take a look. So this compound here, urea, H2NCO, and the Lewis dot structure is drawn above, is widely used in chemical fertilizers. And so the complete Lewis electron dot structure or diagram for the urea molecule is shown above. So part A of this question, this is a 10-point problem. So it's multi-parts, and we're going to spend some time talking about each part. So even in one question that's parts A through G, every single question could, ask about a different topic. And so the first question is asking, identify the hybridization of the valence orbitals of the carbon atom in the urea molecule. And so hybridization of molecules just means how many p orbitals do you have on your carbon, essentially available to make form bonds. And so the definition of hybridization gets more complicated once you actually start learning organic chemistry, but for a introductory level like AP chemistry, you'll see here that if you have a tetrahedral carbon, or you have a carbon where you have 4 individual bonds, this is always going to be sp3 hybridized. So that just means that one s orbital is hybridizing with 3 p orbitals to form 4 new sp3 orbitals. And all of these are coming out in a tetrahedral form, and so about 109.5 degrees between every bond angle. If you look at an sp2 hybridized carbon, now you'll notice that you'll have 1 double bond or a pi bond coming out of the carbon. So this means that you have 1 s orbital and 2 p orbitals coming together and hybridizing to form 3 sp2 orbitals, and that means you have 1 leftover p orbital, which can now form a pi bond or a double bond with an adjacent atom. And if you have an sp hybridized carbon, this means that you're hybridizing now 1 s orbital and 1 p orbital to form 2 sp orbitals, and you'll be left over with 2 p orbitals, and each of those can form a new pi bond, right? So at first, when I was learning about orbital hybridizations, it didn't make much sense to me, but now if you just kind of think about it in terms of how many pi bonds you have, so an sp2 structure is always going to look like, C with a double bond and 2 single bonds, and sp is always going to look like C with 1 single bond and 1 triple bond. And so if we look at the structure of urea, we'll look at that carbonyl group, or that C double bond O, and notice that this carbon has 1 pi bond and 3 sigma bonds. So it should be sp2 hybridized, like I've drawn. And so I'm showing you the exact answers that were provided by the AP Chem exam. So if you write an answer like this is what would be awarded full credit. So 1 point for sp2 without any explanation, but important to recognize. And if you're looking at the nitrogens are actually both sp3 hybridized, because the lone pair actually counts as being in an sp3 orbital. And so if you look at nitrogen like we did in the beginning, like ammonia, where it's trigonal pyramidal, that nitrogen lone pair still takes up a spot in an orbital. So there are actually sp3 hybridized nitrogens, and the oxygen has a double bond and 2 lone pairs. And you could imagine each lone pair has a single bond. And so the oxygen would actually also be sp2 hybridized. And the oxygen in water that has 2 single bonds is sp3 hybridized. So the hybridization is not unique just to carbon. It could also ask about nitrogen, oxygen, other atoms as well, right? So for part B, urea has a high solubility in water, due in part to its ability to form hydrogen bonds, which we were discussing earlier, which is the strongest intermolecular force. A urea molecule and 4 water molecules are represented in the box below. So now you could draw one dashed line to indicate a possible location of a hydrogen bond between a water molecule and the urea molecule. So whoever is drawing right now, I don't know who they are, but they just got it right. So now you're going, again, the definition, recall from earlier that a hydrogen bond is a bond between 2 molecules resulting from an electrostatic attraction between a proton, H, in one molecule, and electronegative atom, O, N, or F in the other. So for example, again, water, ammonia, hydrogen fluoride. So there's actually 2 possible answers here because urea has hydrogens or protons and so does water. So in the answer provided by AP Chemistry, they drew the dash that was just drawn earlier on my screen. Again, I don't know who's drawing on my screen, but thanks for getting it right. You have an oxygen here represented by the water, and you could form a hydrogen bond interaction between the H on urea and then draw the dashed line to the oxygen on water. Also, you could draw
sorry, Chris, that's me. I'm fixing it. Okay. Go ahead. Bye.
Thanks. So a dashed line should connect a hydrogen atom in water to a nitrogen or oxygen atom in urea, or an oxygen atom in water to a hydrogen atom in urea. So you could also draw the other possible hydrogen bond shown there, right? So there's 2 possible answers that you could do here. And so, hydrogen bonding, of course, is not, limited to just the examples I had earlier. In your DNA and the incredibly complicated, proteins, there's huge hydrogen bonding networks that are extremely complicated. So this is a phenomenon that is observed everywhere, and it's happening in your body right now. So this equilibrium reaction represents the dissolution of urea, and is represented by the equation above. Excuse me. So now a student determines that 5.39 grams of urea, which has a molar mass of about 60, and if you didn't know that, you could also calculate it from the periodic table. It could dissolve in water to make a 5 milliliter saturated solution at 20 degrees Celsius. So now we're asking you calculate the concentration of urea in moles per liter in the saturated solution at 20 degrees.
And guys, I just want to remind you, please erase that piece right now because we're going to disable the share screening if you keep doing it. So please erase it right now. Okay, go ahead, Chris.
Thanks.
Don't touch the screen.
So now to calculate moles, the way to do so is always grams of a sample divided by its molar mass. And to calculate molarity, capital M, it is always going to be moles of a substance divided by liters, not milliliters of a solution. So if you want to find molarity, you could either do millimolars over milliliters and then the units work out, or you just do moles over liters. So in this case, we're given 5 milliliters, so you're probably going to have to convert it to divided by 1,000 to get the correct liters, right? So in this case, we're just doing 5.39 grams over the molar mass 60, and you get about 0.09 moles. And then you could divide that by 0.005 liters to get 17.9 molar solution. So again, 1 point is earned for correct number of moles, and then 1 point is earned for correct molarity. And so if you got your units wrong and you did moles divided by milliliters, then you would not receive the second point. So be extra careful when you're doing these unit conversions, and always keep on the lookout for them. And so another important thing to recognize about these short answer questions is that usually they're building off of the previous question. So C, the answer of C can be used in answering part D. And so it could be a problem if you get stuck early on in a question and you don't know how to answer it because the next problem requires you to know that answer. So this is an example here. So D says the student also determines that the concentration of urea in a saturated solution at 25 degrees Celsius is 19.8 molars. So based on this information, is the dissolution of urea endothermic or exothermic? So again, you're going to see a lot of thermodynamics in this test. So justify your answer in terms of Le Chatelier's principle. So again, this is combining equilibrium, so Le Chatelier's principle, with thermodynamics. So you're seeing a bunch of topics interconverting with each other here. So based on the answer from the previous question, we see, which was about 17.9, we see that an increase in temperature results in an increase of molarity, right? So we're going from 20 to 25 degrees Celsius, and we're going from 17.9 molar to 19.8 molar. So you're increasing molarity when you increase the temperature. And so if you're increasing temperature, that means that you're adding heat into the system, right? So this means that this is an endothermic process because you're adding heat into the system. And so an increase in dissolved urea concentration versus an endothermic process gives rise to this solution. So the increased solubility at higher temperature implies that the dissolution of urea is endothermic. If a saturated solution of urea is heated, then the equilibrium is stressed, and then the stress is counteracted by an endothermic dissolution. So if I was, again, to look at this equilibrium equation on the top, it's just Le Chatelier's principle, and it's endothermic. So you're doing solid urea plus heat, and if you're adding more heat, then you're going to drive the equilibrium to the products, to the aqueous phase. So again, being able to recognize equilibrium equations and applying Le Chatelier's principle, and like we did right here, you'll see in either a multiple choice question or a free response question. So that would be the answer there. So again, recognizing endothermic versus exothermic based on temperature differences and knowing Le Chatelier's principle, you need to know both of these to answer this question. Now, part E is kind of like an experimental question. So the equipment shown above is provided so that the student can determine the value of the molar heat of solution for urea. Knowing that the specific heat of the solution is 4.18 grams or joules per gram times degrees Celsius, list the specific measurements that are required to be made during this experiment. And so to answer this question, it could look pretty difficult at the surface because you're just being given, I don't know, bottle urea balance, a bunch of weird, a bunch of miscellaneous lab items, but you would have to know what actually goes into solving for the molar heat of solution for urea, which is actually, could be kind of an involved process. So step one in calculating this, you're going to use the Q equals MCAT solution or equation that we saw earlier. And this question is kind of interesting because you don't actually have to do the math. You just have to know what values to measure, right? So Q is the amount of heat or energy released or absorbed. M is the mass. C sub G is the specific heat capacity, which you're given. And then delta T is the change in temperature, right? So in terms of properties that you have to measure, you have to observe a change in temperature. So you should be able to calculate using a thermometer the change or the temperature at the beginning and then the temperature at the end. And also you have to find the mass of your solute and your solvent. So you're going to use your balance as well. So the next thing is that you have to calculate moles of solute. So moles is usually represented by N. So that's equal to M, the mass of the solute, divided by the molar mass, which you could calculate based on the periodic table. And then step 3, to actually find the enthalpy of solution, or the heat, is going to equal to Q divided by the number of moles, right? So in this case, you don't actually have to plug in for any of the math here. All you have to say is that you need to know the mass of urea, the mass of water, the initial temperature of water, and the final temperature of the solution to actually plug into all of these values. So experimentally, you can find what M is, you can find what delta T is, and if you know about all of these properties, then you could just plug in to your equations and find out the molar heat of solution for urea, which luckily, you did not actually have to plug into your calculator in this case. So memorizing these values or equations could also be useful. So moving on for part F, the entropy change for the dissolution of urea, so delta S of solution, is 70.1 joules per mole times Kelvin at 25 degrees Celsius. So using the information in the table above, calculate the absolute molar entropy S naught of aqueous urea. So in this case, this is a simple math question. So you would just have to know that generally when you're finding delta S of something, it's always going to be products minus reactants. And equilibrium, it's products over reactants. So when in doubt, either divide products by reactants or subtract products from reactants, or the other way around. And so delta S of solution is going to be product or entropy of the aqueous form, because that's what you have in this equilibrium reaction, subtracted by the reactant or entropy of the solid form. Right, so you could just set up this very simple equation. So delta S equals S of the aqueous form minus S of the solid form. And you'll have 70.1 equals, this is an algebra question. So you could just say this is X. So 70.1 equals X minus 104.6. And then you'll find that the absolute molar entropy is going to be positive 174.7. So again, if you had this the other way around, you're doing solids minus aqueous, then you're going to get the opposite sign or a wrong number. So keep in mind, when in doubt, products minus reactants. 1 point is earned for the correct answer. So now that's a math question, but then, moving on, the test is going to make you use your particle level reasoning or intuition to explain this thermodynamic property. So why is delta S of solution, why is it positive for the dissolution of urea in water, right? So again, let's think about the definition of entropy. So you need to use your intuition of thermodynamics here. Remember that a delta S or a positive entropy difference for a system means that the disorder is increasing. So a solid phase material is highly structured and ordered, so it has very low S value, while dissolved particles are free to roam around in solution and they're quite disordered. They have a high S value. So in your response, you should say urea molecules in solution have a greater number of possible arrangements than in solid urea. So things in solution versus a gas, you have to think about actual disorder and how disorganized your molecules are. If you have a solid crystal of urea, all the molecules are perfectly interlocked in place. That's actually the definition of a system that has zero entropy would be a diamond at 0 degrees or at 0 Kelvin. So if you have a diamond and you freeze it, then all the carbon molecules are perfectly aligned in place. It has zero entropy. It's a perfectly ordered system. And that's actually one of the laws of thermodynamics. And that's the definition of how we define zero entropy. So the increased number of arrangements corresponds to a positive delta S of solution. If you're going the other way around and you're starting with, let's say, aqueous urea and you're converting it into solid urea, if you switch that, then the entropy of the system would decrease. So you have to keep in mind, which way you're actually looking at. So what's the product side, what's the reactant side, and consider that when you're calculating for delta S. And then finally, for part H, the student claims that delta S for a process, or the entropy difference, contributes to the thermodynamic favorability of the dissolution of urea at 25 degrees Celsius. So use the thermodynamic information above, or all of your answers and the information provided by the question above to support the student's claim. So you know that the student's right because you're supporting their claim. So keep in mind, if you don't understand what thermodynamic favorability means, you're kind of stuck for this question. So thermodynamic favorability is just kind of synonymous for spontaneity or Gibbs free energy. So whenever you see the words thermodynamic favorability, you should think about delta G, which could be something that you miss. So when we are talking about the spontaneity earlier in terms of Gibbs free energy, this property refers to the thermodynamic favorability of a process. So all that means is it's going to happen on its own at, let's say, a room temperature. If you light a sheet of paper on fire, it's just going to go. The whole reaction is going to go. You combust everything. It's a highly spontaneous, highly thermodynamically favorable process. So if delta G is negative, so you have a negative Gibbs free energy difference, then the reaction is spontaneous, and that's a little typo there, and thermodynamically favorable, and vice versa. So we use this equation that we had earlier, delta G equals delta H minus T delta S, to rationalize your answer. So remember from that multiple choice question, we said if you have an exothermic process or negative delta H, and you have a positive entropy system, so positive delta S, then you're always going to have a negative delta G value. In this case, we said earlier that this is an endothermic process. So we know that delta H is actually positive. So how do we counteract that and make the sign more negative? So the thermodynamic favorability for a process at standard conditions is determined by the sign of delta G. So again, negative meaning spontaneous and positive meaning non-spontaneous, with delta G equals delta H minus T delta S. So since delta S in this process is positive and you're increasing entropy, the T delta S term makes the value smaller, right? T is always positive, and in this case, S is positive. So if you just multiply two positive numbers together, you get something positive, and you're subtracting it. So now you're making a negative. So the higher that delta S value is, then the more you're going to offset that delta H, and the more spontaneous or thermodynamically favorable your process will be. So even though you have a positive delta H at a specific temperature and a high enough delta S, you could still get a negative value of delta G, just not at all temperatures, right? So you have to mix and match and think about that. So this is a very intuitive question and requires you to understand how to explain this important equation to actually receive the points on this answer. So again, the T delta S term makes the value of delta G smaller or more negative, thus makes the dissolution more thermodynamically favorable. So you have to be able to rationalize your answers, quite eloquently and get your points across. So, get some practice in actually writing out, coherent and good responses. So now for number 2 in this test, we're going to be talking about the molecular formulas of diatomic bromine, chlorine, fluorine, and iodine, which are written below. So circle the formula of the molecule that has the longest bond length and justify your answer in terms of atomic structure. So all of these are linear molecules, so you just have Br bonded to Br, or Cl to Cl, etc. And you should consider this question in terms of periodic trends. So recall that atomic radius increases down a group. And you might see questions pertaining to electron affinity or ionization energy as well. So remember, for atomic radius, if you're going down a group, you're actually increasing the radius because you're adding more subshells. So you'll go from 3D to 4D to 5D, for example, and you're making the atom larger. And then atomic radius actually decreases across a period because you're increasing the nuclear charge and attracting electrons closer to the nucleus, right? So in this case, even though it's a little small here, I2 has the longest bond length because the radius of the iodine or iodine atom is greater than the radii of the other halogen atoms, right? So based on this trend, you know that iodine is the lowest halogen and it should have the largest radius. So thus the distance between the nuclei of atoms in I2 is greater than in smaller halogens. So this is understanding periodic trends and being able to rationalize your answer on that basis. So moving on, there's a little bit of electrochemistry here, which we're still going to talk about. So a chemistry teacher wants to prepare Br2, and the teacher has access to the following 3 reagents. So NaBr aqueous, Cl2 gas, and I2 gas. So using the data in the table above, write the balanced equation for the thermodynamically favorable reaction. So again, this phrase, thermodynamically favorable, shows up in 2 questions, meaning spontaneous, negative delta G, that will produce Br2 when the teacher combines 2 of the reagents. So justify that the reaction is thermodynamically favorable by calculating the value of E for the cell of the reaction. And E is the electrode potential, or the voltage, which is related to Gibbs free energy through the following equation. Delta G equals negative NFE, where N is the moles of electrons transferred, and F is the Faraday constant, which you're given in your reference sheet. Thus, to get a negative delta G value, or thermodynamically favorable, you're gonna have to have a positive E value, right, based on this equation. So a positive E is gonna give you a negative G, and vice versa. So E of a neutral reaction can be calculated by subtracting the electrode potential of the oxidized species from the E of the reduced species. So this is also an important definition. Recall, oxidation is the loss of electrons, and reduction is the gain of electrons. You probably heard of Leo says Ger, so loss electrons, oxidation, gain electrons, reduction. And reversing the reaction, or switching where the electrons are, flips the sign of E from, let's say, in this case, you're given reduction potentials, you're adding electrons on the left. If you switch that, and then you'll have 2Cl minus gives you Cl2 plus 2 electrons, for example, then you're changing the value from positive 1.36 to negative 1.36, right? So the answer here actually involves combining two half reactions. So always two half reactions, you have some species getting oxidized, some species getting reduced, right? So if you need something that is thermodynamically favorable, that means you need a negative delta G value, so you need a positive E. So you need to subtract a larger number, so you do big number minus small number to get a positive value, pretty much. So as shown here, kind of skipped some of the work, but to get this actual balanced equation, you'll notice that Cl2 is the reduced species because we're adding electrons, and that's 1.36. Now, for the oxidized species, I have to flip the equation. So now I'm gonna get 2Br minus gives you Br2 plus 2 electrons. If you add these equations together and just add everything on the left with everything on the right, you'll notice that the electrons cancel out, and you'll get this neutral net ionic species, or net ionic equation. So you get 2Br minus plus Cl2 gives you Br2 plus 2Cl minus, right? And so E of the cell, or the standard electron cell potential, is gonna be E of the reduced species minus E of the oxidized species. So you're gonna do 1.36 minus 1.07 in this case. So that also involved recognizing what it actually means to have a thermodynamically favorable process when we're talking in terms of electrochemistry. And so because E of the reaction has a positive value, the reaction is thermodynamically favorable. So you have to be able to get the math right, and then, well, you have to get the equation, which can be difficult if you can't recognize what half equations are. So basically with half equations, you always want to cancel out electrons. And again, I was under the impression that electrochemistry is on your exam, so I have another electrochem question coming up, which we'll still talk about. So moving on, Br2 and Cl2 can react to form BrCl, and the boiling point of Br2 is 332 Kelvin, whereas the boiling point of BrCl is 278 Kelvin. So explain this difference in boiling point in terms of IMFs, or intermolecular forces, between molecules of each substance. So recall the following definitions of intermolecular forces. So in terms of London dispersion forces, which is the weakest in general, not in this case actually, the weakest IMF is a temporary attractive force that results when the electrons in two adjacent atoms occupy positions that make the atoms form temporary dipoles. So generally for symmetrical nonpolar molecules like Br2. Dipole-dipole forces, which we have not talked about yet, it's one definition I missed earlier, that's why I'm bringing it up now, is the second strongest IMF after hydrogen bonding. And hydrogen bonding is just an exceptionally strong dipole-dipole force, if you think about it. And they are attractive forces between, I'm not sure why it has a bunch of white scribbles on it, but between the positive end of one polar molecule and the negative end of another polar molecule. So BrCl obviously has a dipole across it because the electronegativity of chlorine and bromine are slightly different. And so it's a polar molecule. So in terms of intermolecular forces, the only intermolecular attraction in Br2 is actually London forces, and Br2 is a liquid at room temperature. which you might expect it to be a gas like the other halogens, but it's actually a liquid, while those at, for BRCl include both London forces and dipole-dipole forces. So however, due to the greater polarizability of the electron cloud of Br2, you can imagine this is a pretty huge molecule actually. So you could have a lot of London dispersion polarizability going on compared to that of BRCl. So the London forces in Br2 are actually, in this case, stronger than the combined intermolecular forces in BRCl, which usually you might not suspect. You'll always usually think that a dipole-dipole force is stronger than a London dispersion force, but in this case, it's the opposite, and they're asking you to explain that, which could be tricky if you're stuck thinking one is always greater than the other. It actually matters on a case-by-case basis. Thus, the boiling point of Br2 liquid is greater than that of BRCl because it has stronger intermolecular forces, because it has great London dispersion forces. So again, 1 point is earned for identifying the intermolecular force in each substance, and 1 point is earned for a valid explanation, right? So again, keep in mind, know your 3 intermolecular forces: London dispersion, dipole-dipole, and hydrogen bonding, and then know about your atomic interactions like covalent bonding and ionic bonding, right? So now the compound BRCl can decompose into Br2 and Cl2 as represented by the balanced chemical equation below, right? So you have, again, another equilibrium reaction going on here, and then you have a positive delta H, which would imply an endothermic process. And so a 0.1 mole sample of pure BRCl gas is placed in a previously evacuated rigid 2-liter cylinder or container at 298 K. Eventually, the system reaches equilibrium according to the equation above. And so now you have to calculate the pressure in the container before the equilibrium is established. This is extremely similar to one of the multiple choice questions we saw before. Again, this is simply the ideal gas law, PV equals nRT, piv nert. So you could just plug and chug away. So again, solving for P. If you had to solve for V, just make sure you get your algebra right. You could be given 3 of the variables plus the constant, and then you have to figure out the 4th, right? So now, again, in this case, you're actually plugging in the math, and you'll get 1.22 atmospheres. So 1 point is earned for a correct pressure, right, with consistent units. Okay, so this is just plugging in a basic equation. Now, for writing an expression for the equilibrium constant, KEQ, for the decomposition of BRCl. So again, we were talking about this earlier. It's always going to be, products over reactants. So recall again from earlier that setting up an equilibrium equation, like I said, always involves concentrations of products over concentration of reactants. However, for gases, the concentrations can be replaced by partial pressures, right? So the stoichiometric coefficients can now become the exponents again. And then you could do these equilibrium equations for gases actually in 2 forms. So KEQ could be concentrations. So if you're using brackets, that's always going to be concentrations of bromine and chlorine or whatever else you're looking at. Or you could do it in terms of pressures. So the pressure of Br2 times the pressure of Cl2 divided by pressure of BRCl squared, right? But the math comes out the same. You could just substitute molar concentrations for pressures and atmospheres. So 1 point is earned for the correct equilibrium expression. And so the next part is probably the hardest part, and that's why I'm mentioning it here. So after the system has reached equilibrium, 42% of the original BRCl sample has decomposed. So determine the value of KEQ for the decomposition reaction of BRCl at 298K. So this question in particular involves something called an ICE table. So the I in ICE stands for initial concentrations of products and reactants, which you're usually given. C stands for change in concentration, which could be either positive or negative, and is related by the balanced stoichiometric coefficients, like we'll see soon. And then E stands for the concentration at equilibrium. So this is the summation of the initial and change rows. So concentrations can be substituted for pressures when dealing with gases. So you don't always have to be dealing with concentrations. In this case, this is how we set up the ICE table, right? So we have ICE. So the initial pressures in this case, you're starting with the answer from the previous question, right? You calculated 1.22 atmospheres in the beginning before equilibrium is established. So you're starting with that initial pressure of BRCl, and you're assuming that no Br2 or Cl has been generated yet. So you have zero pressure of the products. Now you have a change during the equilibrium reaction. And so due to the stoichiometric coefficients that we have here, if you're subtracting two molar equivalents of BRCl, then you're also generating 1 molar equivalent of Br and 1 molar equivalent of Cl2, right? So you're going to get minus 2x of the change for BRCl based on the stoichiometric coefficients of the balanced equation, and then you're adding plus x for Br2 and Cl2. Now, in the end, you have to calculate the end equilibrium pressures. So now pressure of BRCl decomposed, we have 42% of the original. So now you could do 40.42 times 1.22 atmospheres and you'll get 0.51 atmospheres. So that's the end, or how much of your BRCl has decomposed. So you're going to subtract 1.22 minus 0.51 to get 0.71 at the end equilibrium pressure. Now, to solve for x, we know that 2x equals 0.51 atmospheres because that's what the difference has turned out to be. So you could solve x equals 0.26 atmospheres. So you could substitute in plus x on both sides. So you'll get 0.26, 0.26, and then 0.71 for bromine. And this is after the equilibrium is done. So after 42% decomposition. I would appreciate if all this blue text went away, but thank you. So now we have KEQ equals 0.26 times 0.26 over 0.71 squared. And I'm just getting that by plugging into this equation that we have here. So we have the pressures for KEQ from our previous equilibrium reaction. And now when we plug those in, we're going to get 0.13.
Guys, I just want to remind you to not write. Erase that right now. We're going to disable it. Do not touch the screen right now, or else because we're allowing people to write in the screen and we're going to disable it. Please stop.
All right, thanks.
All right, let's go.
Anyway,
Thank you.
now,
Get rid of the I love you, Chris, right now. Now. Out. Yeah, I know we want kids to have an option to be able to work here. Let's go. Come on, keep going.
all right, so note in terms, the solution is in terms of pressures. If you were to calculate all of this based on molar concentrations, you would actually
And
get,
everyone, let's take a minute. Wait, take a deep breath. Let's take a deep breath. Everyone, at the end, we can write a big thank you to Chris on the slides, okay? Let's keep, but sit tight until 8 o'clock. 7:50, we'll pause. Go ahead.
all right, thanks, Francis. Anyway, what was I saying? So now if you were doing this in terms of molar concentrations instead, so just moles or molarity based on concentrations instead of pressure, then you would still end up with the same answer. But in this case, it's actually easier to figure out in terms of pressures. So again, if you are able to set up your ICE table, you'll get 1 point earned for the correct stoichiometric values at equilibrium, and then 1 point earned for a consistent value of KEQ based on which way you calculated it. Okay? So now in the end, you're going to calculate the bond energy of the BRCl bond in kilojoules per mole using delta H for the reaction, which is given to be 1.6 kilojoules per mole, and the information in the following table. So this could also be important to know. The enthalpy of a reaction can be calculated by subtracting the total energy of the bonds formed in a reaction from the total energy of bonds broken in the reaction. So again, bonds formed subtracted from bonds broken. So now you would set up this equation. So you're given what delta H is equal to, and then you have to calculate what the summations are for bond energies broken and bond energies formed. So you're having 2 molar equivalents of BRCl being broken. So you do 2 times BRCl bond energy, subtract that from one Cl-Cl bond being formed and one Br-Br bond being formed. So now you add these together and then subtract it from 2 times Br-Cl bond energy. So now, you just plug that in, solve for the Br-Cl bond energy, which is just a little bit of manipulation of your numbers, and then you'll come out to 219 kilojoules per mole, which makes sense. Somewhere in between a chlorine-chlorine bond and a bromine-bromine bond would be the energy of a bromine-chlorine bond. So that number makes sense. So 1 point is earned for a correct calculation of the Br-Cl bond energy. So if you remember this equation, then you'll be good for finding out enthalpies of reactions based on bond energies. And then finally, the last question is going to be a bit of an electrochem question. This one's shorter, so I could be able to cover it in about 10 minutes. So now a student is setting up a galvanic cell at 298 Kelvin, and this is from the 2018 exam. Student is setting up the cell at 298 Kelvin that has an electrode of silver solid immersed in a 1 molar solution of Ag plus aqueous, and an electrode of chromium solid immersed in 1.0 molar solution of Cr3 plus aqueous, as shown in the diagram above. So a student measures the voltage of the cell above and discovers that it's 0, which obviously doesn't really make sense. So identify the missing component of the cell and explain its importance for obtaining a non-zero voltage. So you have to be able to look at the cell and realize that everything is in place, but we're actually missing one piece that's not drawn in. So the actual galvanic cell looks like this. So you're always going to have your anode and your electrode. So anode is where oxidation occurs. So zinc is getting oxidized and giving off electrons. The electrons go through the circuit, picked up on the voltmeter reader, comes down to the other side, and then reduces a copper plus solution onto a copper electrode to make a solid. Now, the part that you're missing is that you actually need a way to balance the charge of ions, because you're shooting over electrons on one end, so you need to be able to balance that charge with ions somehow. So the use of a salt bridge between the 2 electrode cells can actually accomplish this purpose. So you always need a salt bridge in a galvanic fuel cell. So again, in the answer, the salt bridge is missing. Salt bridge allows for migration of ions. So you could have sulfate ions and zinc ions, go over through this salt bridge and be able to balance charges. If you didn't have it, then you cannot quench these charges. You'll just be pumping electrons to one end. You can't balance it. There's no more thermodynamic driving force, and then the voltage stops going through. Now, these are the last 3 questions. A student adds the missing component to the cell and measures the standard electron potential of the cell to be positive 1.54 volts. As the cell operates, the silver plus ions are being reduced. So use this information and the information in the table above to do the following. So now calculate the value of E naught for the half reaction, so for chromium 3 plus 3 electrons, right? So remember the following equation for the electrode potentials of cells. So you have E cell is always the standard electrode potential of the cathode minus the anode. So if you're plugging in for these values, then you're gonna get, I actually forgot to include the table. That was just a copy paste error on my part, but it's given that the standard electrode potential of the cathode, so in this case for the silver half reaction, is going to be 0.8 volts. So minus x, and again, this is just an algebraic equation, solve for x, and you'll get that the standard electrode potential of the chromium reduction is actually negative 0.74 volts, right? So again, a reduction meaning you're adding electrons on the left-hand side. So now for question 2, you're going to have to add the 2 half reactions to make a balanced net ionic equation. So again, you're going to have Ag plus 1 electron gives you Ag silver or solid. I didn't write that in, my apologies. And then, so you're trying to make a balanced net ionic equation. So make sure moles of electrons in each equation are equal. So you have 1 electron for the silver reduction and 3 electrons for the chromium reduction. So you would have to multiply the entire silver reaction. Ag plus 1 electron gives you Ag solid times 3. So you get 3 Ag plus 3 electrons gives you 3 Ag solids, right? So when you do this in the end and you add the half reactions So remember, you add the reduction of the half reaction, higher electrode potential, to the oxidation reaction, which is the lower electrode potential. And we just calculated that the chromium one is negative and the silver one is positive. So again, of course, silver is the reduced species, and it also says that in the question. So you're going to get 3 Ag plus chromium solid, and then all of your charges balance out. So you have chromium 3 plus, and then you also have 3 Ag plus on the left. So positive 3 on the left balances positive 3 on the right. And the stoichiometry also works out. And then finally, if you want to calculate the value of delta G, you could use this equation, delta G equals negative N Fe, to calculate the correct value. So you're just plugging in. This is something we saw earlier. So N is moles of electrons. So in this case, for your half reactions, you're doing 3 electrons. So 3 moles of electrons times the Faraday's constant, which you're given in your reference sheet, times the voltage, which volts is actually just joules over coulombs. So 1.54, which you're given at the top. And then this comes out to be negative 4.46. So again, even if electrochemistry is not on your test, which I don't think it will be, this is still something that's worth knowing. And if I knew that ahead of time, then I probably would have picked out some different questions, but I didn't. So that's on me. Anyway.
Actually, that's on me. Sorry, Chris. Okay, my bad. Go ahead.
So thank you for all your attention, and best of luck on your exam, and stay confident.
Yeah, guys, I want to let's take a few minutes just to take a deep breath and to wind up. You definitely have some admirers, Chris, in this chat. Listen, I think it's important, Chris. Would you be comfortable? And I realize I'm putting you on the spot here. Would you be comfortable? Thank you for writing thank you in the chat, everyone. That's really important, because remember, I asked him literally on a quick phone call a few days ago to do this. So I'm just reminding you that this was very last minute, and I really just want to thank you for rising to the occasion. Lots of admirers. Everyone, pay attention for a moment. Chris, do you mind sharing, because there are a bunch of 16, 15-year-olds, do you mind kind of just like telling them a little more about yourself, like more of your background? Because I don't want them to think that you're this like expert chemist and you always knew chemistry. Do you mind sharing, like, kind of, if you don't mind, a little bit of just hardships of your own personal journey? And I'm very familiar because, you know, we went through Queller Prep and we worked on the applications and the college applications together. I think it's just a really nice idea to kind of close things together by letting them know more about yourself, and like it wasn't like an easy ride, you know, your path.
Yeah, I mean, I was saying earlier, you know, this has been a tough challenge for me. I came from a pretty poor family in Forest Hills. I grew up.
Chris, let's take a minute to disable the share screen now. I think we're done with that that lovely sentiment. Thank you, guys. That was very encouraging. Okay, but as we're writing, thank you. But go ahead, as you were saying.
Right. So yeah, when I was growing up in Forest Hills, I didn't come from a rich family or anything. My grandmother and my mother were both immigrants from Buenos Aires, Argentina. So I'm actually a first generation student, and I have a sister who's 5 years older than me. And when we were growing up, she was always very, you know, on top of school and everything. Eventually, she did great on her exams, and in school, she was actually salutatorian at Forest Hills High School 5 years before me, and she went to Yale University. And at that time, when I saw her get into Yale, I really didn't think that school was going to be for me. Like, I liked going to school, but I never thought I wanted to become an academic, of course. I didn't even know chemistry at the time. I didn't even know what carbon was. So, you know, seeing her was definitely a huge inspiration for me. Seeing all the sacrifices that my mom and grandma made to come to this country and be able to support me was a huge deal. Overcome, you know, some rough relationships with like my dad and stuff like that. I'm not saying this was an easy road by any means.
Yeah, and I think it's important to share that. Like, this was not, you didn't have an easy journey, and your sister's not a chemist, and your mom or your dad, like, this is not something they are into. Go ahead.
No, and I think the most important part of getting tutored, and if you send your, you know, this is to the parents, if you send your kids to, you know, expensive tutoring centers and stuff, it's really them at the end of the day who's taking the test, who's studying. Like, you need to have that internal motivation. It can't be forced. you can't just force yourself to like school and want to study. You have to have this natural drive. And as much as it hurts sometimes, sometimes that pain of studying is good because you come out stronger on the other side. Like when I was studying for my SAT and everything, I mean, it sucked. Like I didn't want to learn hundreds of words and stuff like that. Like I didn't want to be doing math problems every day, but I just had to do it because I knew it was the way to reach my goals. Right. So I bit the bullet. I spent all my weekends in that tutoring center instead of having fun with my friends and stuff. And I came to Qualler Prep and I was devoted, and, Francis saw a lot of potential in me, and eventually I became a tutor. And, a year later I got my, perfect math score, and I was teaching SAT math for just years, so I just became even better at it. And
can you add about how that's just about your journey to Caltech? Do you mind quickly sharing what schools you applied to? I think it'll be really helpful for the group. Okay.
Yeah. So at the end of high school, I applied, I think, to maybe 7 or 9 schools. I applied to, at the time, my dream school was UC Berkeley. And I always knew I wanted to go to California to get away from New York for a bit. I actually did not get into UC Berkeley. I did not get into Columbia the first time I applied. I did not get into Yale, even though my sister went there. So when I got those rejection letters, I was really, felt beat up. I didn't even get into Macaulay Honors Program. But somehow, miraculously, I got into freaking Caltech, which is a crazy, science school. Like, I'm to this day, I'm kind of surprised that I got in. And I also got into University of Michigan for their engineering program. And I got into Carnegie Mellon University. And I think Binghamton and Stony Brook as well. Those were my backup schools. And, I just had some stroke of luck that I got into Caltech, because this is like, it's ranked to the #1, school in chemistry literally in the world right now. Like,
and then you were flown in, right? They paid for your airfare and travel.
Yeah, they paid for everything. They paid for my visit weekend. I went 3 days to California. They gave me, another thing that Francis hooked me up with was this really good financial aid assistant. And, Caltech tuition is extremely expensive. It's like $74K or something. And, with this financial aid helper, like we got the tuition down to like $20K per year or something, which is like just a fraction. So that also made school affordable for me. So, thanks to my dad for paying for tuition and everything. But now at Columbia, everything is paid for. I'm on a dean's fellowship. So I go to school for free. They actually pay me to come here. So this is my job. So I teach organic chemistry as a profession. Like, I don't even look at myself really as a student anymore. It's like I'm a teacher, instructor, researcher. I'm getting paid.
And then if you guys have any questions about what he does currently at Columbia, do you want to type it into the chat? I could read it out. But I think it's important to add that right now, you yourself, you're en route to becoming a professor at this path. So do you mind sharing how many students you teach at Columbia at the school?
Yeah, so I have taught, so at Caltech, I was a organic chemistry teaching assistant. By the time I was a junior, because I actually placed the highest at Caltech for organic chemistry. I got 3 A+ in a row, which is probably to this date like my greatest academic accomplishment. And one of my top professors, his name's Gregory Fu, he's one of the top 40 organic chemists in the nation, personally asked me to teach for his class. And when you have someone like that on your back, like, you have all the confidence in the world. So even though I was teaching kids who were literally my age, I was TAing and I was 20 at the time, like, I felt on top of the world just teaching other Caltech students. And it's a small environment, so they always come and ask me for help. So it would probably be 40 students in the Caltech courses, so 30 to 40 students. But now at Columbia, it's huge. Like, I teach classes with over 180 people in it. It's a much larger school. So
and do you mind sharing how old you are right now?
I'm 23, and the people who take organic chemistry at Columbia could be anywhere from 18 years old to like over 40, because they're applying for med school.
So you're 23 right now. When are you going to finish the PhD program?
4 more years.
Everyone
so
pay
27.
attention. Ask about this. This is a good path for you to explore. And then so by 27 you'll have the PhD. And
Yeah,
then what are you thinking after that?
What am I going to do after that? I want to get a postdoctoral fellowship. So a postdoc is 2 more years at another university doing more research. So hopefully I could go to another great school, like another Ivy League or something, for another 2 years and do more research there. And usually after your postdoc, you either go in the chemistry field, you'll work in industry. So you'll work for like a med tech company or a pharmaceutical company. And that's how you make, 6 figures starting salary. Or you try to become a assistant professor at a school. So you'll go and you'll get interviewed by schools and present your PhD research and your postdoc research and your original research ideas. So it's actually really competitive to become a professor. And I get to see as a student at Columbia, like firsthand, these people getting interviewed. So even some of the most brilliant scientists will get rejected from Columbia and they'll only take one person a year. And that person might not even have to accept their offer. So it's kind of like a hard job to get.
They're asking what your research idea is in the chat. What's your research idea?
So my current research in my lab, so I work for Tom Rovis, who's the main organic chemist at Columbia, and I do synthetic organic chemistry. So I do specifically organometallic chemistry, which means I study the chemistry of metals. So I develop catalytic reactions. So basically I take metals like rhodium and iridium on the periodic table, I make catalyst out of them, and then they'll do interesting transformations, like they'll break carbon hydrogen bonds and make new carbon nitrogen bonds. And then we usually take these catalytic methods and apply them to drug design. So you could have some very complicated drug molecule that you want to make, and if you have a proper new method for it, you might be able to cut 5 steps out of your synthesis and have some easy reaction to do instead. So I'm a method man. I do methodology.
So we just want to give you a big round of applause. Everyone, let's type thank you, clap, bravo. I think it's fair to say that everyone in the group wants to say that they love you very much. And I guess you've definitely formed a bond during this time. So we do want to share that. It's important that you shared your journey. You were not necessarily a top performing student in high school. You really just became one through your own hard work, your merit, and your own path. Chris is actually the definition of someone who's really self-made in the field and in the industry in which he studies. So I think that's very important in terms of role models and mentorships. You really carved your own path, and believe it or not, there were at max around 120 in the chat and around 170 who are, going to receive the distribution of your slides. We're just really, really thankful that you did this, and we all want to, say thank you to you for this time and energy and commitment, and under all these, unique circumstances that we have right now. So
No, I definitely appreciate
huge
it.
bravo.
I hope to meet you all in person at some point.
We really want to say thank you. There was a very big school representation. Everyone is saying thank you, including every single student here would like to say thank you. And Oscar definitely wants to lead the way by saying thank you for leading
thank you,
this
Oscar.
wonderful event. And as a group, we do want to say that we're very, very happy that you are hosting this. I do want to just say we're really glad that, as a tutoring company, not a food company or a gaming company, we want to say
it's all real. Like I swear to God, I feel like other, academic institutions will just, they're just looking for the money. It's easy to make money off of tutoring and charging a lot, but Qualer Prep is different because we actually care. We care. If Frances cared, then I wouldn't have continued with the program, but I've been here, and here I am, 7 years after meeting her, and I still feel that way.
And I do want to, just say it's really been an honor being like, I guess part mommy, part observing you really grow. And I've known you since you were 16 years old. Yeah. And forgive me for saying this, he was struggling in math. So look at where he is now. Just remember that it's possible to achieve what Chris achieved, even if you don't, he didn't start with a 90 or you really, really rose and rose and rose. I actually have your report card, your high school report card on display at Queller. So thank you very much for rising, for being where you are today. And you're really young and very ambitious and accomplished. So we're going to close up by saying that this was a huge success. You did a great job.
Thank you.
Thank you, Chris. We're gonna send this recording over, and I hope everyone just, gets a lot out of this. And it's been an excellent experience.
Yeah, I'll
hosting
send,
the webinars and
I'll email Frances my slides and she can send it to everyone else.
absolutely. And Chris, you're getting a ton of thank you messages from everyone. A lot of thank you messages from the kids.
Yeah, no, thank you all for, spending your time tonight.
And yeah, we just want to say thank you. And those of you who are entertaining us, we just want to say we're really, really glad that you're here and, participating in this. So that's it. What can I tell you? Besides, it's 8:03. We've made it very far. Thank you. You've been great. And I think we're good. So we're going to send this recording over in just a little bit. I guess we'll have it from here. All right.
All right. Thanks a bunch.
Anything else? Okay, Chris. So you're going to hit end meeting. Okay.
All right. Goodbye, everyone.
All
Have a
right.
good
Let's
night.
go, everyone. Thank